So now when we look at a particular transition metal complex, the question is, how can we analyze the orbital energies and how can we fill in its electrons? So let's take, for example, a chromium 3+ complex. So first, we're going to look at a free chromium atom. And we can have an energy scale. If we look at a free chromium atom, we have our 4s electrons and our 3d electrons. In a free chromium atom, there are 6 valence electrons. Those valence electrons are going to fill in these orbitals, giving it the lowest energy configuration possible. Chromium was one of the exceptions to the normal counting rules, so it's going to be an S1 D5. So this is our free chromium atom. The question is, when we put chromium in a complex, so let's just say I have Cr H2O6 3+. What happens to the energy level diagram when I look at this complex? So if we're going to compare these, what's going to happen? The first thing that we need to do is visualize the structure and then visualize how the d orbitals interact with the ligands. In this case, we have 6 ligands that are going to give us an octahedral structure. The oxygen in the water is going to bind directly to the transition metal. I'm going to leave off drawing the H's here just because I'm lazy. And this is how we typically would draw these complexes. So in this case, I have 6 ligands interacting with the d orbitals on that chromium. So we have 6 H2O ligands. We're going to form, these 6 ligands are going to form a strong interaction with the dx squared minus y squared and the dz squared. There's going to be a weaker interaction with the dxy, the dxz, and the dyz. Because in this case, in an octahedral molecule, all the ligands lie directly on our Cartesian axis. In terms of the s orbital interaction, we're going to have a very strong interaction with the s orbital. And remember, these are repulsions because we're looking at the electrons on the ligand interacting with electrons in the transition metal. So if we now look at an energy diagram for Cr H2O6 3+, the strongest interaction here is the 4s orbital. So it's going to be repulsed the farthest, which means it's going to be the highest in energy. The next strongest interaction is going to be the dx squared minus y squared and the dz squared. These orbitals right here are called degenerate orbitals. And degenerate means they have the same energy. The weakest interaction, or the lowest energy orbitals, are going to be the dxy, the dxz, and the dyz orbitals. These are also degenerate. And when we characterize these, we can say that the x squared minus y squared and the z squared are doubly degenerate, and the xy, xz, and yz are triply degenerate. Simply meaning that a doubly degenerate case has 2 orbitals with the same energy. A triply degenerate case means we have 3 orbitals with the same energy. In this case, we have chromium 3+, which means we have 3 valence electrons. Whenever I put these valence electrons in the orbitals, they are always going to fill the orbitals, which gives us the lowest energy configuration. We're still following Hund's rule, which means we go spin up all the time before we go spin down. And we put these 3 orbitals in, or these 3 electrons in the triply degenerate set of orbitals that's formed when we have our octahedral complex. So this is kind of what happens here in this particular case. One of the things that I have to mention and is very important in this diagram, this is our energy scale. It's the change in energy between these sets of orbitals that is very important, and it's going to lead to the color. This delta E we're going to refer to as the delta O. And the delta O is the octahedral field splitting energy. So if you see delta O, that means we have an octahedral complex. In an octahedral complex, there's going to be a splitting of the d orbitals. So all 5 d orbitals aren't the same energy anymore. They're going to split. And they're going to split into 2 different sets. The lowest energy excitation now is going to be to take an electron from here and to excite it up to here. That excitation, that absorbance energy, the lambda that we can look at, typically happens in the visible portion of the spectrum. And we call this excitation, right here, a D to D transition. Because essentially we're going from a set of orbitals that has D character to another set of orbitals that has D character. So this is kind of what's happening, right? And this allows us then to figure out differences in color. The color of these transition metal complexes, or the magnitude of the delta O, is going to depend on several things. The first thing it's going to depend upon is the oxidation state of the transition metal. The second thing it's going to depend on is the electronegativity of the transition metal. And the third thing it's going to depend on is the ligand. If we look at several common complexes with chromium as the transition metal center, and we look at Cr F6 3-, the color we observe is going to be green. If we look at the color that's absorbed, remember the color that we see to our eye, the absorption is going to be its complementary color. So that means the absorption for this particular complex is going to be in the red region of the visible spectrum. If we have Cr H2O6 3+, the color we see with our eyes is violet. That means the absorption is in the yellow region of the spectrum. If we have Cr NH36 3+, this is a yellow color. That means the absorption has to be in the violet region of the spectrum. The absorption energy is directly related to the delta O. And on Friday, we'll begin our lecture with the spectrochemical series and figure out how that's going to influence the color. I would highly, highly, highly recommend to you guys that you read the last section of chapter 24 before you come to class on Friday. It will make Friday's lecture make a lot more sense, and that's going to be the content that's